Okay, maybe it's time to get started. Sounds good. It's kind of a weird room, isn't it? We have a small course and a huge amphitheater. I hope you'll speak up when you ask questions. And also, you didn't preserve locality, so I need to look here, and then look here, and then maybe look here. Now this is the definition of random access. Okay, anyway, it doesn't matter. We have whatever room we have. At least it is capable of recording, which is good. So you had the first instance of the seminar last week. Mohammed, who is probably here. So, oh yeah, he's over there. See, that's the downside of random access. It's hard to find the data you're looking for at low latency. Okay, Mohammed covered the first lecture, and I'm going to cover today. We're going to go through some more examples, some more of the course logistics, and give you some examples, presentations of what kind of things that we're expecting in the course, and hopefully it'll be interesting as well. So remember that our key goal is in this course, is to learn how to rigorously analyze, present, and discuss papers and ideas in computer architecture. And there's a lot here. Hopefully we're going to achieve this. And clearly there are some sub-goals. Thinking critically is important. And I think this is really necessary at this time for anything that you do. It doesn't matter whatever you do in the world. Thinking critically, you can do much better. Thinking broadly, especially in computer architecture today, as Mohammed covered last time. This I already said in the previous slide. And get familiar with key first steps in research. And also understanding research papers. Even if you're not going to do research, it's good to keep a good idea, have these skills to evaluate new ideas, whatever you do in life. I actually have a lot of friends who don't do research, who work in, I don't know, product design, in engineering, or not engineering. It could be different areas like architecture, design. They read a lot of research papers to get ideas, and they need to do exactly what we're going to do in this course to evaluate the potential benefits of those ideas in what they do. This also applies to medical fields. This also applies to pharmaceuticals, banking maybe. I don't know enough about that area. It could potentially apply there. But certainly in the technology-related fields, you will have to do a lot of reading. And reading may be technical or non-technical, but you'll have to process what you read somehow. And at some point, you'll have to present what you read or what you develop to other people. So it's good to know exactly all of these that is on this slide. And get familiar with key research directions. That's also good. Okay, so these are actually slides from last lecture. So I'm going to go through these relatively quickly. Basically, how do we achieve the key goal? We're going to use an algorithm. Basically, there are some steps for the presenter. Presenter is going to read, absorb, read more, critically analyze, think, synthesize, and prepare a clear and rigorous talk, present, and answer questions, and analyze and synthesize during the lecture at the course end. I'm going to talk about that a little bit more later. And participants are also involved in this. It's important. And in real life, you have both roles, right? You'll be the presenter sometimes, and you'll be the participant sometimes. So it's good to understand the both roles and figure out good algorithms for it, algorithms that fit you yourself, so that you can achieve the best out of these presentations, whether you're a presenter or a participant. So in this case, participants will discuss, ask questions, and also analyze and synthesize. Okay, so a little bit about the logistics. Hopefully everybody submitted homework 0. That's a way of getting to know you. I haven't looked at them yet, but even if you missed the deadline, you're welcome to submit. You can submit. We'll wait for that. And please explicitly provide paper references. I think most people provided them. There are a couple of people who didn't provide them, so please provide paper preferences if you haven't done yet. Don't say that the deadline is passed, so I cannot provide it. Well, if you don't provide it, then there's no way we're going to be able to assign you a paper. So please do this as soon as possible. So we will have 2 presentations each week we meet. We'll determine the schedule after we get all the preferences. So each presentation basically will be done by one student. It'll be on one paper. They'll be the discussion lead. We'll expect a 30-minute summary plus analysis and a maximum 20-minute discussion plus brainstorming plus feedback. So we'll have ample time for discussion, hopefully. This will be fun. So please do not, try not to exceed 30 minutes. If you do it by a couple of minutes, it's okay. But 30 minutes is ample time, actually, to present a paper. Okay, and please follow the suggested guidelines, and I'll give you a couple of examples today. So it's clear that there's no class next week. Depending on how many students we get preference from, there may be no class the week after that also, so that you can prepare for your first presentations. Make sense? Okay. Okay, so these are some course requirements and expectations. Attendance is required for all meetings. There's a sign-in sheet. I think this is good because this way you can get a picture of everything else. You actually learn by presenting, but sometimes you learn even more by watching someone else present. You can learn what are the good things that you can do and what are the things you may want to avoid. Again, this is also personal, everybody. There's no single perfect algorithm to do one thing in the world, the presentation, for example. You need to adapt your presentation skills to yourself and how you feel comfortable as well, right? But by observing many of these presentations and many of these discussions, you can adapt to that much better, I think. Okay, we already said this. Oh, okay, mentors, yeah, there will be mentors who will help you prepare, and I think this has been very helpful in the past for students, especially those who haven't done technical presentations before. Getting that feedback from a mentor after 2 meetings really makes your presentation better. Okay, now I already said this also clearly. Of course, if you're a non-presenter, you'll be more effective if you skim or read the paper beforehand. Reading may be too much because these are long papers. But if you could at least skim the paper beforehand, that would be helpful. I would suggest, though, so how do I skim papers? When I want to quickly get an idea of the paper, clearly I look at the title. It's good to read the title. And then the abstract, and then the intro. And maybe the results and the mechanisms a little bit. I will, if I have only 10 minutes to read a paper, I will not go through the results, for example. But I will go through, skim through them, and then look at the conclusions also. Basically, try to find those places in the paper where you can get the key ideas, key novelty, and key mechanisms very quickly, and the key results very quickly, of course. If it's a well-written paper, this should be really easy to do in 10 minutes. By the way, think of this also as an opportunity to understand how you can write papers. Even though we're not going to write papers in the seminar, the reading that you do and the understanding that you develop based on the papers that you read can help you become a better writer, because there are some papers that are much easier to read, and there are some papers that are much harder to read. And usually you can figure out which papers are good, easy to read papers if you try to skim the paper in 5 minutes and try to get all of the key ideas and key contributions quickly. If it's a well-written paper, you'll get out most of that quickly within the abstract. You'll get a lot of information from the title, and then a lot from the abstract, and a lot from the intro, so that you'll be done in 5 minutes. Okay, so there's an online review system, which I think is actually a little bit cumbersome. I don't like how it's done in Moodle. So this is going to be optional. We'll expect comments on papers in the review system, and this will affect, although grades are not the most important thing, this will be an optional grade, basically, for you after the presentation. And people have enjoyed discussions in the past seminar courses, so if you're interested, I would suggest doing this. Okay, and then there's a synthesis report at the end of the semester, which is hopefully fun, and there's a sample synthesis report online. You can take a look at it. You can see the type of questions that you expect. I don't expect this to be something long. In the end, there are a bunch of questions, but they're easy to answer. So take a look at it online. Okay, so grading rubric very quickly. Again, this is a seminar course, and actually, in any course, it's good to have the perspective of learning before the grades, right? It's important to learn. Again, I'll make a comment that I like making these days. Think, let's say, 30 years ahead. 30 years later, whatever you're doing, what will matter more to you and others? Will your grade matter? Who will care about that at that point? No one, actually. Or will the insights that you've taken and the learning that you've generated out of this particular course matter? I hope the insights and the learning will be much more important 30 years. Even if you may not believe that right now, it is true, actually. With that long-term perspective, it is absolutely true. Even if it's a very, very little insight that you glean, it's going to be remembered much more than the particular grade that you get. Anyway, basically presentation is important, as you can see. Clearly, this is an evaluation of the presentation. How well did you understand the material? How well did you present it? How well did you answer the questions? technical terms, okay. And we'll take into account the difficulty of the paper and the time you had to prepare for this. Time you had to prepare in the sense that some students will have less time to prepare their presentation because their presentation will be scheduled earlier in the semester, and some people will have more time. But of course, that'll be small effects. I expect everyone to do well in this course, frankly. And the second part is quality of this final synthesis paper. And you can see the synthesis report example online. And there's also attendance over here. So attendance is important. I think a good seminar is good if people attend the seminar and participate. Okay, and as I said, there's a bonus that's added if you participate both during class and online, especially. Okay, any questions? Okay, hopefully that's clear. So, okay, I like expressing many things as algorithms, and there's an algorithm for paper presentation also. So we'll go through this. Basically, we cover this actually in lecture 1 for the presentation guidelines. And it looks like this, basically. You read and analyze your paper thoroughly, discuss with anyone you wish, use any resources. You're completely free. Mentors are good resources also. You prepare a draft presentation based on guidelines, and then meet mentors and get feedback, revise the presentation and the delivery, meet mentors again, and get further feedback. So it's good to have 2 meetings so that you can actually improve in between. And revise the presentation and delivery again. And meetings are mandatory. It's for your benefit. You can skip them, actually, but usually what happens is if you skip them, your final presentation here will be worse than what it could be. Your mentors are there to catch the things that are easy to catch. And invariably, the presentations improve with feedback. And practice also. Practice is the other one. So if you do everything else wrong, practicing may still be able to save you during a presentation, if you practice a lot. In fact, what I suggest to my students sometimes is to practice in front of a mirror, especially if they don't like speaking publicly. Go in front of a mirror and speak to yourself. Present the entire presentation. I've done it a couple of times. Actually, if you have time, I'll give you the presentation where I did it once. But I'm not sure if we will have time for the second one over here. Okay. So what we will do today is to go through some example paper presentations, because learning by example, as I said, is a good form of learning. And if you're very good at learning by example, you can learn much faster. Because you can only do so much, right? You have a very limited amount of time. But you can see a lot more, and you can hear a lot more. So if you can process that information and learn by example and apply that to yourself, it's much better. So Mohammed already did one last lecture, memory channel partitioning. Do you remember that? Okay, good. So I'm going to do something else. At least one more. Let's see if we have time for 2. So this is the structure of the presentation. This is the structure that I'm going to follow, and this is the structure that we provide as guidelines for you. And I would suggest following this guidelines. It's a very well-tested method. Over more than a decade, I've used it, and it works, basically. Okay, so I'm going to actually show the slides, show this in unrolled slides. Basically you talk about the background, problem, and goal, talk about the novelty of the approach, talk about the key approach and the ideas a little bit, talk about the mechanisms in some detail, give the key results with methodology. It's good to talk about methodology a little bit, and then talk about the key results in terms of evaluation, and then summarize the paper at the end, give the takeaways, well, at least summary takeaways. So this part is essentially the summary of the paper. And then you go into strengths. What are the strengths of the paper in bullet points? Starting from the most important one to perhaps the least important one. It's always good to order the strengths in terms of what's most important to what's least important. So for example, conceptual things are more important than others. Oh, this is a completely new idea that has changed the thinking in the field. Right? That's probably more important than this idea improves performance by 2x. So conceptual versus evaluation. Conceptual is almost all, actually, I will argue that it's always more important than the evaluation part, because evaluation is always limited, right? You evaluate the idea as you envision it at that point in time, but concept itself can affect centuries, right? That concept may be employed for a long time. So it's good to keep things in perspective. What's more important, what's less important. Strengths. Writing very well-written paper is also a strength, for example, but it's probably not as big of a strength as the concept, the novelty that it brings. It could be a very well-written paper on a topic that's not important, right? Okay. So weaknesses, this is actually where you think critically. Strengths are usually easier because usually authors try to anticipate the strengths. Not always. Sometimes they are not as able to anticipate the strengths or put them in writing, as well as the analysis that you can make. But weaknesses, usually authors don't want to anticipate the weaknesses or don't want to tell you as much about the weaknesses. That's a weakness of the process itself, scientific process, unfortunately. So this is for the reviewers or the readers to actually figure out. If the paper actually does cover some of these, that's great. That's actually a strength of the paper in general. Papers that talk about the limitations and weakness of the approach are stronger papers, in my opinion, compared to papers that do not. Of course, you have limited space in a paper. That's why some papers don't include those. But this is where you need to actually think hard, think about the weakness. And again, most important weakness first. What is the most important weakness in the paper? Think about a fatal flaw, for example. And usually conceptual weaknesses are the biggest weaknesses. Right? For example, if the paper solves a non-problem, that's clearly a weakness, right? Of course, now you need to think critically, and you'll have to be able to argue that this is a non-problem. It's not a problem. This is a solved problem. And the paper's approach will not be effective because the problem is not important. So as a reviewer, you'll need to be able to make that argument. Well, hopefully the papers we assign don't have that problem, that particular weakness. But if you find that out, that's good. Of course, there are other weaknesses, like the evaluation is not complete, or the paper doesn't really explain things really well. Yeah, we'll see some of these. Or there could be things that the paper didn't consider in the solution, right? Okay, and the paper is horribly written, could be another weakness. And usually that's important sometimes, right? Especially if you really want to have good impact, you would like to have a paper that's really well written and strongly written. And you'd like to be able to reach many people. People should be able to understand the paper quickly and get the ideas quickly. And if the weakness is that the paper is horribly written, it takes 5 readings to understand it, that's probably not a good paper. It may be proposing a great idea, actually, that could have a lot of conceptual novelty and impact, but it may actually not have that impact because it's not written well. I actually know of several papers later in the semester, maybe I'll tell you a couple of them. Because they're not written so well, because they don't explain the concept as well, they're not as convincing. As a result, they didn't have the impact they could have. So later papers have been written on the same conceptual idea that have had a lot more impact. Even though the conceptual idea is the same, the writing is much, much better, the evaluation is much better and comprehensive. As a result, they actually are credited for having that idea. It's a bit unfortunate, but that's also how it is. Okay, so after weaknesses, it's good to talk about thoughts and ideas. What are the thoughts and ideas that you may have on the paper? You can become creative. It's okay, this is brainstorming. So let's see what comes. I'll give you examples of this also. And then final takeaways. And then you can open it up for discussion. It's good to always have some points to ignite the discussion, like ask the people in the room, or what do you think about this particular aspect? Or if the solution, will this solution work, for example, 30 years from now? It's always good to ask that question, maybe. Or will this still be important 30 years from now? It's good to have that long-term perspective. Okay. Any questions? So I've given you a summary. Now let me actually demonstrate this with a real example review that I will do. I will follow the guidelines mostly. Maybe I'll steer away in some couple of places. But it's for the fluidness of the presentation, not because I don't want to follow the guidelines. Okay, I'm going to cover this paper, RowClone. Fast and energy efficient in DRAM bulk data copy and initialization. Has anybody heard of this? I know some of you have. No? Okay, that's good. So it's going to be new to you. Clearly you didn't read the paper because you haven't heard of this. So it's not going to be as similar to the discussion that we will have, but please feel free to ask questions. And whenever you're actually talking about your paper, always introduce your paper like this. Provide the title, where it's published. It's published in Micro in 2013. It's written by my PhD student, Vivek, and a bunch of students in my group, as well as collaborators from Intel. And we're going to talk about that. And I'm going to use some of the slides that Vivek had prepared for his presentation at Micro, and some of the other slides that I have prepared. So it's going to be a combination of multiple things. It's going to be fun. I like this idea. And this was part of Vivek's PhD thesis, one of the ideas in his PhD thesis. Okay, so let's start with the guidelines. We'll start with the background problem and goal. Let's define that first clearly. So basically, if you look at today's systems, you have multi-core systems, and you have memory attached to a CPU. And this memory channel tends to be a bottleneck because many applications are data intensive, and this doesn't have enough bandwidth, and it's long latency, and it's very energy hungry. So it has limited bandwidth. I already said a bunch of this, high energy. So the goal of this paper is to reduce the memory bandwidth demand. And it's in general a good goal if you want to have a good system, because you want to exercise this memory bus as little as possible because it doesn't have enough bandwidth, it has high energy. So we want to reduce the unnecessary data movement in this work. And this work tackles two key things that affect data movement: bulk data copy and bulk data initialization. Bulk data copy is when you copy a bunch of source data to a bunch of destination locations. Let's say you're copying a page to another page, 4 kilobyte page. Well, or you're copying a 2 megabyte page from one location to another location. Bulk data initialization is a special case of copy. You can think of it that way. You basically write a value to a destination. And let's say you're initializing a page with all zeros. It's called zero initialization. Many operating systems, for example, do initialize pages to zeros so that they don't leak information about the data of one process to another process when they allocate that page to some process. So that's called bulk initialization. And these are actually similar things. So if you can think about initialization, it's actually a special case of copy, because you can think about the source page, let's say, being all zeros, and you copy all zeros to the destination, right? That's why initialization and copy are very similar to each other. Okay, so people have written a lot of papers saying that bulk data copy and initialization are actually important in real systems. They're a bottleneck in the design of operating systems, for example. If we had fast ways of doing this, it would be nice. This is actually a relatively old paper from 1990, I think. Another paper, well, this has a date over here, another paper from 1990, saying why aren't operating systems getting faster, as fast as hardware? Because there's not good enough support for simple primitives like this, page copy and initialization. Because operating systems actually use this a lot. Whenever you, for example, fork a new process, you need to copy the data that it needs. Whenever you fork a thread, you need to copy the data that it needs from the main thread to the thread that you're forking. And that could be a lot of copies. Whenever you're initializing a database, for example, you need to initialize a huge amount of tables, depending on the size of your database. Whenever you're allocating a page, you need to give 0 pages to users so that you don't leak information, as I said, for security and privacy reasons. And you want to do this fast, essentially. And there are some recent papers that also talk about hardware support for this. Okay, I'm spending more time than I would normally spend so that I can give you the background. So this is more like a lecture, in a sense, but I'll try to speed up. So bulk data copy and initialization is actually useful for other primitives. I already discussed forking, zero initialization, checkpointing. You copy pages of a process to some other location so that if the process is executing and a fault happens, you can go back to this checkpoint. So you need to have a checkpoint of the memory. So you may need to copy a lot of pages over here, cloning a virtual machine, deduplication, and migrating some pages. These are all require copies of large amounts of data. Of course, it depends on the data set. And recently, this is actually a paper that's on the reading list that you could select from. Google published an analysis of all of their data center workloads, and they've shown that in all of their workloads, about 5% of the cycles is spent on just 2 system calls, memmove and memcopy. And these are just a fraction of the data movement. These are 2 explicit system calls that you do to move data and copy data. And they show that 5% of the entire execution cycles average across many of, according to them, all of their data center workloads is spent there. So this is a lot, actually, 5%. It's good to always keep the 5% in perspective. In real life, 5% is a lot because this is averaged across a lot of workloads, real workloads. Sometimes you may see papers that claim a lot of benefit. Actually, I'll give you a real example over here. In the 1990s, late 1990s, power efficiency of processors, microprocessors, was a big research topic. It's still a big research topic, but at that time, for example, there used to be papers published in academia saying that, okay, I do this little tweak in the processor, and I get 40% reduction in energy of many workloads. Now, as a skeptical reviewer, you should probably say, how do you get 40% reduction across many workloads with that little tweak? And that's exactly what Intel said also. Intel published some work saying that, okay, according to us, there is no part of the processor that spends more than 5% energy consumption. Basically, it's relatively equally balanced. So there's no single trick that would give you 40% performance benefit. This doesn't mean that it doesn't exist, but it's very unlikely that you could do this little tweak and get 40% very quickly. So it's good to keep this in perspective. These real studies are useful in that sense. And whenever you see big numbers, question them. This doesn't mean big numbers don't exist, but you should be aware of why those big numbers come about. Okay, so let's get back to the topic. The topic is bulk data copy initialization. So how do existing systems do bulk data copy initialization? I'll give you a pictorial example of copying a source page to a destination page. Today, if you would like to do this copy, you need to go through the processor. Basically, the processor brings the source page byte by byte all the way into the L1 cache, brings the destination page byte by byte all the way into the L1 cache, does the copy, write, and then writes the results back into memory, byte by byte. Now, this is high latency because you need to go through this round-trip latency 3 times. High bandwidth utilization on the memory bus, which is a bottleneck. This causes cache pollution, but you could eliminate that by setting up this copy through the direct memory access engine, which is present in pretty much all memory controllers today. But it has some overheads also. And it causes unwanted data moment, because if you're going to copy the source page to a destination page, and if you're not going to use the destination page for a long time, you're basically bringing all this data into the CPU caches for no benefit, right? CPU caches are there so that you could reuse the data, but if you're not going to get reuse of the data, you just want to copy the source page to the destination page, it basically cause a lot of unwanted data moments. So if you actually do a 4 kilobyte page copy through a direct memory access engine with some technology assumptions that are in the paper, it takes about 1,000 nanoseconds and 3.6 microjoules. So it's a lot of inefficiency. So clearly, if you want to do 2 megabytes, this goes up, right? So let's talk about the paper's novelty, key approach, and ideas. So basically, the paper proposes conceptually at the high level what I'm going to show you now. This. The memory does the copy internally, and it doesn't bother anything else in the system. That's the highest conceptual level right now. So what is the benefit? This is low latency because we're not moving data all the way over this interconnect, and many interconnects here. This is low bandwidth utilization. In fact, no bandwidth utilization because we're not moving any data into the processor. It's all happening inside the memory chip. No cache pollution, but we could eliminate that through by doing this copy through the DMA engine today. We don't pollute the caches if you do it through the DMA engine. And no unwanted data moment. If we're not going to reuse the destination page, we're not bringing it, which is good. So the paper's approach, in the best case, reduces this 1,046 nanoseconds to 90 nanoseconds and 3.6 microjoules to 0.04 microjoules. So let's take a look at how this is done. So I'm going to give you the best case example. Let's go into a little bit more detail in terms of the key approach. So internally, a DRAM chip, like many other memory chips, consists of rows of data. And these rows are connected to a row buffer, which is a row of sense amplifiers that amplify the data. And let's assume the source and destination pages are in what's called this DRAM subarray. The key idea in this case is very simple. You basically activate the source page and then activate the destination page. And those 2 consecutive activates enable copying of the source data to the destination page. Let's take a look at why this happens. The first step, we activate the source row, which brings the data into the row buffer. Now the data is amplified in the row buffer. Row buffer actually captured the data, amplified the data that it saw in the cells. Now the next step, we activate the destination row, which implicitly deactivates the source row and connects what's in the row buffer to the destination row. Now the data that was captured in the row buffer starts getting driven into the destination row. Sense amplifiers drive the data from here to here, and that's how you capture the data inside the destination row. So by doing 2 consecutive activates, you're able to accomplish this copy without moving the data outside the subarray. And that's the key novelty of the paper also. It's a very simple idea, but it was not proposed in the past. And it has negligible hardware cost because in today's systems, you can do activate, and then you need to do a read. Today's systems, unfortunately, do not allow you to do another activate to the same bank. Basically, you just need to enable that other activate to the same bank in existing systems. Okay? So that's it, basically. That's the key novelty. We're going to go into more detail now. This works clearly only if the source and destination pages are in the same subarray, right? But there are many, many of these subarrays in a DRAM chip. Then the question is, how do you actually do that? And those are the other mechanisms that we're going to develop. So let's go into a little bit more detail. So if you look at a DRAM chip, it consists of these banks. In this case, you see a 4-bank chip, and there's a memory channel, and the CPU is connected here, and there's some I/O logic. And there's a shared internal bus over here, which enables movement from the bank to outside the memory channel. And if you look at a bank, internally, bank consists of many subarrays and some I/O logic underneath the subarrays. And if you look at a subarray itself, it looks exactly like what I showed you in the previous slide. It has a bunch of rows, and it has a row buffer. And if, whenever you want to read a row of DRAM cells, you activate the row, which brings the data into the row buffer. So clearly, the source page and destination page, if they're here in the same subarray, things can be very fast, as I showed you. Now the question is, the source page and the destination page can be in different banks. How do we do the copy? And the source page and the destination page can be in different subarrays of the same bank. Then how do we do the copy? Right. So the paper introduces 2 types of RowClone. One is intra-subarray RowClone. It's called the fast parallel mode. In this case, the copy occurs at the row granularity, which may be different from the page granularity, which I'm not going to talk about, but the paper covers that. The second type is interbank RowClone. It's byte granularity copy. I'm going to give you examples of this. It's called pipeline serial mode. And the last one is inter-subarray RowClone, which basically tries to copy from one subarray to another subarray. It turns out this is not very efficient, so later work has developed mechanisms to actually make it more efficient. So let's look at the fast parallel mode. I've already given you this idea. You have the source row. The key idea is to bring the source row to the row buffer first with an activate, and then bring the data from the row buffer to the destination row with another activate. So let's take a look at how this happens internally. So clearly we're going into more detail right now in terms of how the chip operates. So if you look at, I'm going to abstract the source row and the destination row with these cells. If you look internally, you have a single cell over here in the source row. You have a single cell in the destination row. But think of this as row-wide operations. I'm just showing you one cell over here. And this is the sense amplifier. Let's take a look at how we do the intra-subarray copy. First, we activate the source row. So initially, if you want to read from the source row, the bit line over here is set to VDD over 2 so that you can see the reference. And this is the row buffer over here. So if we activate the source row, in this case, it stores a charge state, which may be encoded as 1, for example. What happens is, due to charge sharing, this capacitor, DRAM capacitor, shares its charge with the bit line, and it perturbs the bit line just a little bit. The charge over here is very little. A DRAM cell is very small today, actually. It's very hard to make it even smaller today. Just to give you some perspective, the size of this is more than 100 times smaller than the size of this today. DRAM is designed for very high capacity, so DRAM manufacturers optimize the size of this a lot. So the charge that you can store over here is very little. So when you actually connect the source row to the bit line through the use of the access transistor, basically you activate the access transistor over here, very little charge gets shared between this and the bit line gets perturbed by a little delta over here, but that's enough. With that perturbation, the sense amplifier kicks in and amplifies the difference. And what it does is it basically pushes this bit line to be VDD by doing amplification, and the other side is 0. And then because it pushes the charge to be VDD, it refills the cell with the full charge. It replenishes. This is called restoration also. So amplification and restoration enables this to be filled also. Now we've captured the value of the source row over here. Now what do we do? The next step is to keep that value in the sense amplifier and push it into the destination. The idea is very simple. You do another activate to the destination. Once you do this activate over here, this bit line is fully charged, and the sense amplifier is very strong. Because this bit line is fully charged, it pushes the charge into the destination row. As a result, the data that you read in the previous activate gets copied to the destination row. Make sense? It's very simple. So you may ask the question, okay, this could actually perturb the charge also, but no, because this is not at VDD over 2 at this point. If this were at VDD over 2, yes, this will perturb the charge and pull it down, and the sense amplifier will sense it. But because this is at VDD, full charge, you can push the charge into the destination. Okay, so conceptually, this is what we do. Activate the source row and activate the destination row. And this gives you significant benefits. Latency improves, reduces by more than an order of magnitude, and this is memory energy. Memory energy reduces by almost 2 orders of magnitude, between 50x and 100x, 74x in the paper. And there's no bandwidth consumption, and very little changes to the DRAM chip in this case. Okay, here I give you large numbers, so you should always question the large numbers, where it's coming from. Well, in this case, hopefully it's convincing where it's coming from, but you should convince yourself while you're reading your own papers. Okay, so there are clear constraints to this fast parallel mode. Basically, location of the source and destination is a constraint. Both should be in the same subarray for this to work. Size of the copy, it's at the row level. It copies all the data from the source row to the destination. Sometimes you may not want to copy that much, right? So let's take a look at some other, let's remove some of these constraints. So pipeline serial mode, interbank copy removes these constraints, but gives you less benefit. So let's take a look at this example. You have a shared internal bus between the banks. We're going to copy a source number of bytes from a row over here to another row over here. So how do we do it? Basically this way. We set the source row, source bank into read mode, destination bank into write mode, and pipeline the requests from the source bank to the destination bank through orchestration from the memory controller. So the memory controller decides how many things should be copied from here to here. It could be an entire row. It could be just 1 byte, or it could be anywhere in between. It could be actually copies from multiple rows into a single one over here, but that needs to be orchestrated even more. Okay, so if you actually do this copy across an entire row over here from this bank to another bank, your latency reduction is lower. It's about 2x, and energy reduction is also lower. It's about 3.2x, which is still not bad, but maybe this is not the best way of taking advantage of RowClone. Okay, so the generalized RowClone mechanism, you get intra-subarray 2 activations. You get interbank pipelined copy, pipelined read or write from the bank. And the hardest part is really copying the data from the source subarray to a destination subarray. This is hard because there's no direct connection between the subarrays over here. What you need to do, what's proposed in the paper, is to actually use the interbank copy twice. You first copy from the subarray to a temporary row in some other bank, and then copy from that temporary row to another subarray in this bank where the source row was, but not in the same subarray. So this solution is cumbersome, as you will see in the paper. It doesn't give you a lot of benefit in terms of latency, but it gives you some benefit in terms of energy, because data still stays on the DRAM chip. It doesn't go out to the memory channel. And the area cost is about 0.01% in the DRAM chip if you include all of that. Okay, so I've given you examples of the copy. Let's take a look at initialization. The paper proposes if you want to initialize a row or multiple rows, zero initialization is very common in workloads. So you fix 1 row in a subarray to all zeros at some capacity loss, and you basically copy that row to the rows that you want to initialize. And if you want to do it with arbitrary data, you initialize 1 row and copy the data to other rows. Zero initialization is the most common, as I said. If you do it the way I just described, it gives you 6x lower latency and about 41x lower DRAM energy, with some loss in capacity. You cannot use those rows that you reserve for zeros. But zeros are actually usually good. If you look at some processors, they reserve some registers to be all zeros. In alpha ISA, for example, R31 is always all zeros. It's hardwired. And basically the idea is, in a sense, similar to those registers reserved as all zeros. You have a row in each subarray reserved to be zeros, because this is a common operation. Okay, so this is the summary of the latency and energy benefits, basically in 1 slide over here. I'm not going to go through this in detail. Clearly, the highest benefit comes from intra-subarray copies. And zeroing is an intra-subarray operation, so you get significantly high benefit. And zeroing benefits are lower because you're dealing with only 1 page, right? You're writing to only 1 page. You don't need to bring multiple pages. Okay, and the cost is important. That's going to be an upside of the paper, because this is very low-cost changes to the memory chip. Okay, so the paper also discusses system design to enable RowClone. So you have this RowClone substrate. How do you take advantage of it? at the high level. Clearly, somehow you need to communicate occurrence of bulk copy and initialization from the application across the layers. It's good to think about how it's done. I'm not going to give you all the details over here. Some ISAs, x86 ISA, for example, has a repeat prefix. So you could use repeat prefix to repeat some operation. So if you actually repeat move, there's a repeat move s instruction, then you can actually copy arbitrary amounts of data with a single instruction from one location to another location. But not all ISAs have that. How do you ensure cache coherence? If the processor has some of the data cached in the caches, and if you want to write to it, how do you ensure that? The paper says that you should flush the cache, not the entire cache, but just the page that you're operating on from the cache. That's one way of doing it. Maybe there should be more efficient ways. How do you maximize the latency and energy savings? Because clearly the savings that you get is asymmetric depending on where the source page and the destination page are. So if you design an operating system that's aware of the subarrays, it can do much better. For example, when you're doing copy of a source page to a destination page, when you're initializing a thread, the operating system, if it's aware of the subarray level structure of the DRAM, what it can do is it can basically allocate the destination page from the same subarray as the source page. If it can do that, it will maximize the benefits. Right? This paper discussed that very briefly, but not a lot. How do you handle data reuse? We're going to tackle that. So data reuse is, what if the data that you're initializing or copying, the page you're copying into, is going to be needed by the processor very soon? In the baseline case, if you actually go through the processor will have the page inside the caches. But if you do RowClone inside the memory, the processor will not have it. So how do you actually handle this? The paper doesn't fully solve that problem, but it talks about it a little bit. So it's a more general problem, actually. So clearly, there's a lot to do. Even if you have a substrate like this with a very simple, hopefully nice and clean idea, you still need to think about the end-to-end system design to enable it. Okay, let's take a look at some of this. So the paper talks about two new instructions, memcopy and meminit. And it exists in some ISAs, as I said. And basically, microarchitecture needs to be modified to implement it. You need to check if the instructions can be sped up by RowClone. Microarchitecture can do some performance analysis to be able to do that, so I'm not going to talk about that. And it needs to be able to export the instructions to the memory controller such that the memory controller can do it using the RowClone-enabled chip. Managing cache coherence. As I said, RowClone modifies data in memory, and you need to maintain coherence of cache data. So in this case, the solution is very similar to existing systems. You leverage the hardware support for DMA to flush the page that you're writing to. Of course, you can do additional optimizations, and the paper briefly talks about that. And the third point is, how do you maximize the use of this fast parallel mode, maximize the benefits? As I said, you make the operating system subarray aware. And these are two primitives that are used by operating systems that could benefit from this fast parallel mode. As I said, if you're doing copy on write, whenever you're doing a copy on write is a primitive where the operating system needs to copy a page if some other, copy a shared page between threads, if one of the threads is going to write to it. These threads are supposed to have their own view of memory when they're forked. If the thread is going to write to it, then the copy happens. And at that point in time, you can allocate the destination in the same subarray as the source. Or in any allocation point, you can do that. Of course, this requires modifications of the operating system now. Bulk zeroing, again, you use the FPM, fast parallel mode, to copy data from reserved 0 row. Okay, handling data reuse after zeroing. This paper tackles the case where you zero a page, and then you need to reuse that page. Let's take a look at what happens with RowClone. In the baseline, there are two phases, actually. The first phase, OS zeroes out the page, and the hardware zeroes it out also. And the second phase, application needs to use the cache lines of the page. If you think about RowClone, it basically speeds up the phase one. It avoids misses, cache misses in phase one, because everything is done in memory very quickly. But it incurs misses in phase two because everything is done in memory, because it didn't bring the data into the cache. So the question is, how do you get the benefits of both worlds? There's a proposal in the paper that is called RowClone Zero Insert. If you're actually zeroing out some cache lines, and if you predict that you're going to reuse those cache lines, you insert clean zero cache lines into the cache. This is very easy to do, right? Because you're doing the initialization inside the memory. You might as well start inserting the cache blocks as zeros without transferring any data into the cache. Because you don't need to transfer any data because you know that it's going to be all zeros. So it's a clever optimization, but it works only if you know the data values that you're writing. So if you know the data values that you're initializing your cache with, clearly you don't need to bring those data values from anywhere. You just write them into the cache. Okay, so let's talk about, I've given you key results actually, but let me talk about the application level results right now. So the paper uses a simulation methodology to figure out the benefits in real applications. And you can go through this in detail. I'm not going to go through this in detail right now. It uses a bunch of copy and initialization intensive applications and some performance metrics. And these are the applications that it evaluates. So clearly applications are selected to have some sort of copy and initialization. In fact, if you actually use some of the regular benchmark suites like spec, you don't get that much copy and initialization in some of those benchmark suites, even though this is actually a real problem in many applications. Like forking, as you can see, system boot up, it does a lot of initialization and copy databases. Okay, I'll let you study that. So there's a study of the copy and initialization, the fraction of memory traffic caused by zeroing, copying, and regular writes and reads. And you can see that these applications perform significant amount of copying over here, significant amount of initialization over here, zero initialization, and some applications have less and some applications have more. We'll get back to the workloads. You could always argue about whether the right workloads are used. If you remember the rat holes from the last lecture, I'll get back to that rat hole picture. Okay. There's analysis, of course, in these applications. You can read the paper for more detail. So this is the benefit that you get in terms of performance, instructions per cycle improvement compared to the baseline, and the memory energy reduction in the real applications after simulation. So some of them benefit significantly. The shell, for example, benefits about 40%. The forking benchmark, because it does many, many copies, it benefits about 40% in terms of performance improvement. Some of them benefit less, 5%, but 5% is still important, especially with a little change. Memory energy reduction is significant in almost all of them. It's more than 10% in all of them. And improvements correlate with the fraction of memory traffic that is caused by copy and initialization. So if you overlay the previous slide over here with this one, you will see that there's a strong correlation between the bars over here and the bars, the reds and blues in the previous one. Okay, the paper also does an analysis of multi-core systems. Single-core systems is interesting, but clearly bandwidth is a bigger problem in multi-core systems because many cores contend for the memory bus, and you get more benefits. So for example, if you're running a copy and initialization intensive application that's accessing main memory to do copy and initialization, and if you're running some other application that just needs some amount of data, it doesn't do copy and initialization, the application that's doing a lot of copy and initialization actually can destroy the performance of the application that just needs to access memory. So if you actually offload these copy and initialization operations to the memory side, you actually free up a lot of memory bandwidth that other applications can use, hopefully more efficiently, right? For more random access, for example. You really need that bandwidth for random access if you're doing graph processing. You're not doing a lot of copying of the data or initialization of the data. So that's, basically you're using the memory bandwidth for the cases where you really need it if you use this approach. So the paper has some methodology. Basically, half of the cars run copy initialization intensive applications. The remaining half run spec applications that do not have copy initialization. And the paper looks at the performance improvement, system performance improvement, and memory energy efficiency improvement that you would get in different types of systems in simulation. There's more detail, of course. The workloads are described a little bit more in the paper. But as you can see over here, you get significant performance improvements if you are running in this scenario. And this scenario can easily happen in a cloud setting, for example, or in a cell phone setting too. But in a cloud, for example, you may be copying a lot of data with some applications, but some other applications may be doing very important graph processing or machine learning where you don't, where you're trying to find out stuff from the data, right? Okay, so the performance improvement about 15%, and it increases with the core count. And energy efficiency also is significant. Energy efficiency doesn't have a great correlation over here because it has a lot of other things associated with it. Because when you're doing 8 core, when you're running 8 core with the same memory system, you're actually exercising the memory system a lot more. So the energy doesn't only depend on how efficiently. So the overall energy you're consuming is actually a lot more in the memory system. That's why this fraction doesn't increase. Okay, but you get consistent improvement in energy per instruction. Okay, so I've given you basically all the paper almost. I'll finish with a summary. Basically, the paper targets the problem of bulk data initialization, which unnecessarily move data on the memory channel, memory bus, and degrade system performance and energy efficiency. The paper proposed the idea of RowClone, which is conceptually performing copy in DRAM with low cost. The key idea is to at least a key conceptual idea, and the key part of the paper is to use the row buffer to copy a large quantity of data by bringing the source row into the row buffer and then copying the data from the row buffer into the destination row. And this leads to about an order of magnitude reduction in latency of a 4 kilobyte copy and about 2 orders of magnitude reduction in energy for a 4 kilobyte copy. And the paper shows that you can accelerate the copy on write and bulk zeroing, which are important for many applications in the world. And it shows that you get significant performance and energy efficiency improvement in multi-core systems as well as single-core systems with very little overhead in terms of what you need to put into the DRAM chip area. Okay, so let's talk about the strengths. I'll do some analysis right now. The strengths of the paper, it's a simple, novel mechanism to solve an important problem. This is the highest strength that I could come up with. These are all important. It's conceptually simple. It's also a mechanism-wise simple. It's novel. Nobody came up with it until it was published. And it's an important problem. It's effective and it has low hardware overhead. It's an intuitive idea. I don't know how to order this. Intuitive ideas are usually good. And it greatly improves performance and efficiency, assuming data is mapped nicely. So now we're getting into weakness a little bit, maybe. Somebody needs to do data mapping nicely. But if your data mapping is nice, then it gives you great performance and efficiency. And it also seems like a clear win for data initialization, because if you're initializing a page, you don't really have that much data mapping requirements. You just initialize that page over there, right? Of course, there are caveats over here that we can potentially discuss. Okay, let's talk about some other strengths. This makes software designers' life easier. Software designers try to avoid page copies quite a bit, and also initialization as much as possible. But initialization may be hard to avoid sometimes. But copies, they try to avoid a lot. If you go to companies like VMware, for example, where you need to do a lot of copyings of virtual machines, their software stacks are written such that you minimize the page copies. And as a result, the software stack is very hard to read and very hard to maintain. So if you had a solution like this, maybe you don't need to jump through all of that hoops to get rid of copies. Your copies are already fast, so your software stack stays simple. So the paper doesn't demonstrate it, but this is actually a potential strength of the paper that can change the software and algorithm. And these things are very difficult to demonstrate in papers, because now you need to actually show, get a full software stack and rewrite it, assuming that you don't do all of those optimizations, or you write those optimizations and compare your benefits to the optimizations, but those optimizations take a long time to do. It's been honed in companies like VMware. I pick VMware as an example, but any company that does a lot of copying of data tries to avoid that copying of data. Okay, basically, if copies are 10x or 100x cheaper, how do you design the software? How do you think about the algorithms? Okay, paper also tackles many low-level and system-level issues, so it's actually across the stack. Even though it starts with a low-level idea, it tackles a lot of the system-level issues. And I will argue that it's a well-written, insightful paper, but I'll let you, this is my paper, so I'm biased probably. But I'll let you decide that. Okay, let's go into the weaknesses. This is where you need to think critically, as I said. So one of the weaknesses is, and this is an important weakness, it requires data to be mapped in the same subarray to deliver the largest benefits. And if you want to do that, you really need to actually change the system, meaning that if you want to do that transparently to the programmer, you need to change your operating system to be aware of the subarrays. So this requires more changes than actually it looks like it would require as a result. So it helps less if the data moment is not within a subarray. Clearly, somebody needs to do the mapping of the data. And it doesn't help if the data moment is across DRAM channels. So you could argue this is a weakness. I would argue that this is more of a limitation, because this is not a problem that the paper is targeting, right? If your source page and the destination page are in different DRAM channels, clearly moving the data inside a single DRAM chip will not help you. There needs to be some other solutions for that. That's why I think it's good to point this out, let them move on, because this is really not a problem that the paper is trying to solve. But if you think about the broader data movement problem, this is clearly a real scenario. And even though this is not a problem that the paper is trying to solve, there might be real applications that do not benefit from this paper because data is not mapped to the same channels, right? Okay, inter-subarray copy is very inefficient, as we discussed, because you need to move the row to another bank and then from another bank to the other subarray. We're going to talk about that. And there is no solution for this in the paper. You just need to avoid it, basically, by doing the mapping correctly. It causes many changes in the system stack, especially if you want to take the full advantage of the mechanism. And it's an end-to-end design that spans essentially applications to circuits, right? This is a circuit level idea, very low level, but it spans all the way to applications and maybe algorithms. Okay, while it's good to evaluate and develop such solutions, it's really important actually today because it's very hard to come up with solutions that can be employed at a single layer. It's good to look at software-hardware cooperative solutions like this. But these solutions are usually not that easy to adopt because they change many things in the system, right? So adoption is not so easy. Okay, and then cache coherence and data reuse cause real overheads that are not necessarily fully evaluated in the paper, even though the paper handles them, maybe not in the best ways. Okay, and then the next, I keep going through weaknesses. You could actually add to weaknesses also. Evaluation is done only in simulation. You could argue that this is a weakness. But this could be a strength also, because with simulation you can explore a lot. But it's good to think about alternatives as to how you could do it. The reason it was the paper resorted to simulation is because it's very difficult to manufacture a real DRAM chip and put this idea inside there. It takes a lot of effort and time, and sometimes it's not even possible because of the technology barriers. I forgot that cost part of it is also a lot. So simulation is a very good way of exploring ideas, actually. But of course, you should always be careful about the downsides of simulation also. Is it always accurate, for example? Okay, evaluation does not consider multi-chip systems. This could be another thing, or multiple memory channel systems where you do copies across the memory channel. That is true. And you could keep poking holes at evaluation, actually. And are these the best workloads to evaluate? That's another question, right? Maybe the paper didn't evaluate clearly all of the workloads. It evaluated 6 workloads. Maybe there should be other workloads. Maybe some workloads are not as realistic. Fork bench, for example, a paper examines different amounts of data copy that happens when you fork a thread. It's actually good for understanding, good for analysis, but it's really not a real workload in the sense that it's not evaluating the entire system, right? Okay, here we should be careful. Now I could rat hole. And I could talk about all of these evaluation and workload issues, right? It's good to point these out and then move on. It's better not to harp on them. It's a bit unfortunate because in today's review system, when people review papers, they harp on some of these things unnecessarily. Even though some smart people, like who I borrowed this picture from, clearly said these are rat holes. You should just move on. Okay, so I'll spend some time over here. I'll do a digression. Basically, these are things that you can question in any single paper, any single work, actually. Actually, it doesn't matter. It doesn't need to be a paper. Any single presentation that gives you some sort of performance results. And it doesn't even need to be in engineering, actually. I have this new idea, new mechanism, and it brings down the cost of, I don't know, human resources by 500%, 5x. Well, have you evaluated with a real workload? How do you get that 500%, right? What is your metric? Should it really be the cost? Or should it really be, does your metric really take into account really the total cost of implementing this idea? Because there is a sunk cost also at the beginning. Maybe you improve the efficiency by 5x, but that sunk cost may be a lot, right? And then configuration, does it really apply to my company or your company or this particular organization? Will it be 5x in this real situation? And a bunch of details. So you could actually poke a lot of rat holes to any single idea and presentation. So it's good to realize these rat holes. Actually, I just copied this from the paper. This is Rod Jane's book. That's where this is from. This is from his slides, but I think his book is better because some rat holes are bigger, as you can see, than some other rat holes. And if you read this over here, I'll let you read some of that, but even if the performance analysis is correctly done and presented, it may not be enough to persuade your audience, the decision makers, to follow your recommendations. The list shown in box 10.2, which is this, is a compilation of reasons for rejection heard at various performance analysis presentations. You can use the list by presenting it immediately and pointing out that the reason for rejection is not new and that the analysis deserves more consideration. And also, the list is helpful in getting the competing proposals rejected. So people use this list all the time, as you can see. But basically, an analysis can be rejected simply on the grounds that the problem needs more analysis. That's like a chicken and the egg thing, right? Clearly, everything can have more analysis. This is the first reason listed in box 10.2. This needs more analysis. And then workload can be questions. I like this comment over here. The second most common reason for rejection of an analysis and for endless debate is the workload. Since workloads are always based on the past measurements, their applicability to the current or future environment can always be questioned. This is especially true in computer architecture, where you're designing hardware and software systems, computing platforms for, let's say, I don't know, next year or 5 years down the road. How can you anticipate the workload 5 years down the road right now, right? You have the workloads that are real today, but you don't have the workloads 5 years down the road. So you can clearly, easily question this. That's why it's very important to think about the conceptual arguments well. Like if you look back 5 years, there are very few people who would have guessed that you would have these sophisticated machine learning accelerators everywhere, right? And machine learning is a relatively new workload. If you talk to people 10 years back, if you had said, oh, I want stochastic gradient descent acceleration in my general purpose computer and GPU, they would kick you out probably. Who cares about stochastic gradient descent? Who cares about deep neural networks? Those are applications nobody used at that time. Those are actually thought to be not good in the sense that there's not enough computational power and there's not enough benefit. But now, fast forward 10 years, everybody's building this, right? So it's good to think about the workload as something that's not necessarily killing ideas. So that's why I put these rat holes into perspective. Okay, actually, workload is one of the 4 areas of discussion that lead a performance presentation into an endless debate. These rat holes and their relative size in terms of time consumed are shown in figure 10.26. So I don't know how accurate this is. You could actually go into another rat hole by questioning these rat holes, but we're not going to do that. Okay, but I copied and pasted this so that you could benefit from this over here. There are actually some really interesting reasons. They're not just that point to conservative thinking in terms of movement of technology. For example, why change? It's working okay. It's good to think about that, right? It's working okay, but maybe it's not working the best way it could be, right? Or I don't know. That's beyond today's technology. I mean, these are good points. Some of these are good points, but it doesn't mean that the ideas should not be examined. But you hear some of these, actually. Sometimes you hear these in reviews. For example, nobody has ever done that before. That's also interesting. That shouldn't be a reason to examine it. Maybe not. Okay. It's not simple. This is actually sometimes a good criticism, sometimes a bad criticism, but simplicity is sometimes in the eyes of the beholder also, as he comments over here. Okay. And I would recommend this paper, the book also. Have you ever used this book in any class? Okay, yeah, I don't expect because it covers a lot of really great concepts in performance analysis. If you really want to have a go-to book in computer systems, I would definitely recommend it. I guess one of the TAs has used it. Have you used it, Minesh? Okay, good. Okay, now I've digressed a little bit. Let's talk about some thoughts and ideas based on the paper. We're still doing the paper review. And I don't think we're going to do the second paper review today. We could have a discussion on RowClone, perhaps, because we won't have time. So let me go into the thoughts and ideas. So these are some extensions that I have based on my reading of RowClone. Of course, I have the hindsight of being one of the authors of RowClone, as well as teaching this for a long time. But I think you can come up with these also when you read the paper. Can this be improved to do faster inter-subarray copy? Inter-subarray copies are not good with the RowClone method proposed in the paper. Can we improve it? And the answer is yes. And one of my students later asked the exact same question and wrote a paper to improve it. And the idea is, he called it the low-cost interlinked subarrays. It was part of his PhD thesis. It was published in 2016, as you can see over here. The idea is actually simple, conceptually simple also. You have this subarray and you have this other subarray. Today, they're not connected to each other. And the idea is, why don't you connect them to each other? So how do you connect them? You use transistors called isolation transistors that connect the bit lines between the subarrays. And then you can open and close them such that you enable connections so that you can get the subarrays connected or disconnected. And if you do that, now you can copy data from a row in one subarray to another subarray very, very quickly. Almost as quickly as the fastest mechanism that we have in RowClone. Not quite, but almost. It's actually much better than doing interbank copy because you're utilizing the wires again. Just the wires are longer, and you need to do the isolation transistors. You need to enable the isolation transistor to do the copy. So it's a beautiful idea. It enables other things also, actually, if you do that interconnection. Okay, can this be extended to move data at smaller granularities? I don't know if there's a solution to this. So the granularity right now is the row granularity, right? It could be 4 kilobytes, 8 kilobytes. Actually, now you're dependent on the granularity of the hardware, which is not necessarily good. The paper has a discussion about that. But can we somehow make this smaller granularity? If you want to move 100 bytes, can we do that as fast as RowClone proposes? Can we have more efficient solutions to cache coherence? Can we minimize the overhead? This is still an open problem, actually. Data reuse after copy and initialization. This is also an open problem. It's also a general problem. This paper is one approach to accelerate particular operations inside the memory, but people have been examining, it's actually a very hot topic today in computer architecture and computer systems in general. How do we offload other functions into the memory side such that the memory does these functions without bothering the processor? Because memory is very efficient at doing these functions because it doesn't need to move the data a lot, right? If you do these functions inside the DRAM chip, that's great. But if the processor needs some of the data produced by those functions, now you run into data coherence issues and data reuse issues. This in general in the processing in memory paradigm. So how do you solve these are still important. Can this idea be evaluated on a real system? This could be another extension, right? How do you evaluate it? I would love to do it, but it requires a lot of sunk cost, for example. The approach that we've been taking is more to have the DRAM manufacturers evaluate on their real systems and then decide whether or not to use them. Even for them, it takes a lot of time to move. Of course, if I were a DRAM manufacturer, I would implement it right away. Okay, can similar ideas and DRAM properties be used to perform computation on data? This is also interesting. Like, we're not doing computation here, we're doing data movement and initialization, right? Can we actually do computation on data? And one of the papers that is listed in your seminar papers is the Ambit paper. I don't know if people will pick on it and present it, we'll see. But the Ambit paper, Vivek's last work in his PhD thesis, that was published in Micro in 2017, 4 years after the RowClone paper, does exactly that, basically. It uses the chart sharing properties, which RowClone uses, as we discussed, to do bitwise AND, OR, and NOT inside the DRAM subarray. And you can take a look at the paper. And it gives significant benefits in terms of the performance and energy of those operations, about 30 to 60x improvement in terms of performance and energy. So clearly this work has led to other works. And actually, if I were thinking, right, if I had more space over here, I would add another thing over here, which is, can you actually use the same ideas on some other technology? Right. Can you do RowClone in some other technology? And the answer to that is also yes. Other people have shown that you could do things that are similar in phase change memory, for example. Okay, so, and these are some of the papers that I just described. This is a low-cost interlinked subarrays paper. I'm not sure if this is on the paper list, but if it's not and you want to pick it, let us know. And this is the in DRAM and an OR paper. This is the early one, and this is the later one. That's the full paper that talks about basically accelerating these block bitwise operations and not OR. And once you have and not, and a not, you can build anything, right? It's functionally complete. Basically, this is a processor in memory itself. You just need to be able to program it and change your algorithms, express your algorithms in terms of block bitwise operations to be efficient. So having said this, I have a comment on RowClone. RowClone essentially does block bitwise copy and initialization, right? Everything is happening bulk and in bitwise. So you're doing the copy. Every bit is independent of each other and they're being copied. This is basically extending RowClone to do AND, NOT, and OR. Okay. And coherence, as I said, is important, and there are some works that target this. I'm not going to talk about this. There's more work to be done in the area of, if you have a processor and a near data accelerator, how do you keep them coherent? And let's say your programmer partitions the program such that some of it executes on the processor, some of it executes on the near data accelerator. Now, if you want the programmer to think less, you would like to keep these two different things coherent with each other, such that if clearly the processor has some caches, near data accelerator may have some caches, and you want to keep those caches coherent. Now, the issue is if you want to use existing coherence mechanisms between the processor and the the accelerator, existing coherence mechanisms are not really designed for doing efficient coherence across the memory bus. They're more or less good at doing coherence on chip, but on chip you have a lot of bandwidth, right? Actually, on chip bandwidth is wasted because of coherence also. But if you actually want to send coherence messages every time you update or read some data, it's a lot of overhead in terms of traffic on the memory bus. You don't want to do that. That's why it's really important to examine the coherence mechanisms for accelerators that are sitting on the other side of the memory bus. Other side meaning the side that the processor is not on. Okay, so let me give you the takeaways. We're almost done. Basically, these are the key takeaways that I have in this paper. It's a novel method to accelerate data copy initialization. It's simple and effective. It's hardware-software cooperative. It has good potential for work building on it to extend it to different granularities. I think this still needs to be done. To make things more efficient and effective, I think this still needs to be done also. And multiple works have already built on the paper. As I said, Lisa, Ambit, and many other works that I cannot put over here, but you can find them easily these days on places like Google Scholar, for example. It's an easy to read and understand paper, but you can decide on that yourself. And the next step after the presentation is done is open discussion. So it's good for the leader, person who presents, to maybe come up with some leading questions like, what are your thoughts? How practical is this? Will the problem become bigger and more important over time? Will the solution become more important over time? These are actually questions that you can ask generically about any paper. I'm just putting these. You can, of course, customize the questions based on the paper also. Are other solutions better? And is this solution clearly advantageous in some cases? And that's the end of the presentation. Okay, so let's do some discussion if you're interested. Since we don't have much time, and I'll leave you early because we didn't have a break in between. We're not going to cover the second paper, but the slides will be available. Any questions? Yes, please. So that's a great question. Improvement in energy consumption is very drastic. It's memory energy, I should rephrase that, but if you're maybe bottlenecked by your memory energy in many systems. I'm not sure if anybody has not tested in real hardware. It may be that some companies have actually looked at this, and they're increasingly more interested in simple solutions like this. So this is very difficult to test in real hardware in an academic setting, because as far as I know, there are zero academic places that do at least cutting-edge DRAM manufacturing, because it's very difficult to do. Industry is far ahead of academia in terms of the manufacturing capability. That's... Yeah. There might be. We don't know. At this point, we don't know. They may have internal prototypes in real hardware. I'm in touch with some companies. They're very interested, but they don't want to tell much, at least publicly. I should say that. That's one reason. The other issue is, actually, there are multiple issues. So you're touching on a very good point. Why isn't it done in academia? We've already handled that, I think. Why isn't it done in industry today? Part of the issue is mindset, and the second issue is interfaces. So for this to be adopted in the general case, you may need some changes to the memory interface. 2 activates, you don't need changes. Actually, it doesn't need a lot of changes, but it requires some change in the mindset such that it needs to be specified in the interface. And that takes a lot of time in memory. That's one of the reasons why it has not been adopted very quickly. So if this was a change that didn't happen on the memory space, but that did happen on just the processor, such that one company could change it and not inform anyone or not coordinate with anyone, in my opinion, it would have been done right now. But because it's changing the interface and some specification in DRAM, adding new functionality, that needs to go through a body called JEDEC, and there are like 100 companies in it, I think. So they need to come up to an agreement. Yeah, that's more difficult, yeah. But these are real issues. They're somewhat unfortunate. But from my perspective, I think if I were a DRAM manufacturer, I would just do it. And basically, there will be people who would adopt it, I think. quickly. And they will be the early adopters, early testers, and they can give quick feedback. And they can say, oh, okay, I benefit or I don't benefit. My expectation is that a lot of people will benefit over time. And that's how you get the new technology adopted. It takes only one brave person to do it. And once that brave person does it, if it's a good idea, everybody will follow suit. Yes? Mm-hmm. Yeah. Mm-hmm. Yeah, that's a very good point. Yeah, the paper doesn't analyze that. So the paper doesn't look at, let's take a look at these real applications and see what fraction of the time the bulk copy happens inside the subarray or across subarrays in the same bank or across different banks. I agree it would be good to do. Now taking my hat, the other hat, the researcher hat, I will say, yes, it's good to do, no question about that. But my expectation is that because today there's no such mechanism, the software is not designed to take advantage of something like that. So the results I expect to get will be, okay, you don't see a lot of copies within a subarray. Because there's no reason to do it within a subarray today. So it's like a chicken and the egg problem. That's always true with a new idea. Because things are done assuming that this doesn't exist. Well, because people didn't know that it existed. They didn't design for it. As a result, the software is probably not going to benefit if you don't rewrite it, such that copies are, happen more often in the same subarray or across different banks in the same chip. But that's a very good question. If I were a bad reviewer, I would use that and say, oh, okay, you didn't evaluate these workloads, and I would, this idea is no good. And I've seen that also. But don't be a bad reviewer. I'm not suggesting that you are. I think your point is very well taken, but this could also be used as one of the decision makers' games. So so the takeaway, I think, is whenever you're evaluating a new idea, it's good to ask the question that you're asking. It's good to understand the workload. But it's also good to say that, okay, maybe the existing system is not ready for this idea yet, so you will need to change some things. And actually, that's true for many ideas that we will examine in this course. Mm-hmm. Yeah, absolutely, absolutely. I think those are actually some research topics that are related to processing in memory in general. This is a very simple form of acceleration in memory, right? It's not doing processing in memory; it's acceleration in memory. But yes, you will need to change. I mean, what you said is true for if you want to work on two different pieces of data in memory. They just need to be close to each other. Yes? Mm-hmm. Mm-hmm. Uh-huh. That's a good question. I don't know. That's a good research topic, probably. So your concern is, would this lead to more vulnerability somehow, security-wise? It's hard for me to tell. It's good to think a bit deeper, and I don't think I have done enough deep thinking. From my gut feeling, it feels like it shouldn't change much in the system, but I don't know what side channels you're exposing if you actually do that. Side channels are a harder one. Ex
So there's no way to like talk directly. So I guess it depends a bit on how the orchestration happens. If this is orchestrated by the memory controller, I guess it's harder for like any kind of software to directly talk to the memory controller.
That's right.
Trigger something that's not allowed.
Mm-hmm.
But if it's on the OS level, like it was suggested in this paper, there might be a way to like.
Yeah. So actually, it's done in the memory controller. So all of the copy is orchestrated by the memory controller. So I don't think you, unless there's a bug in the code, of course, I don't think you can fool the memory controller to do the copy between two different privilege domains, because it's really sent by this is an instruction from a given application, and that instruction gets executed in the memory controller. So I don't think you violate the security boundaries, but you may be causing some other side channels that don't exist today, right? That part is always harder, side channel analysis. So somebody may somehow figure out that you're doing this copy in memory, and if it's privileged code, it can time your code somehow. I don't know. That I haven't thought about. But I think in general, if you can have more functionality in memory to do processing, maybe you can offload some security functions inside memory also. So that could be interesting. This paper clearly doesn't do that. It just opens up the space a little bit. But that's a very good question. I think these questions are very good for discussion, actually. What are the security implications? That's another question that could be asked for many new mechanisms, actually. Especially today, right, with the importance of hardware security with Meltdown and Spectre and Rowhammer and all kinds of attacks. It's good to ask the question. What are the security implications of your new idea? Yes, please. Mm-hmm. Mm-hmm. Yeah, absolutely. So this paper clearly didn't evaluate with GPUs, but there are some papers in the future that looked at doing computation in the GPU memory. I can point you to some. One of them is, we've done some work in this. It's called transparent offloading and mapping. It's essentially looking at offloading some essentially GPU, highly parallel GPU tasks to the memory side. And you gain significant performance and energy efficiency, of course. That was published in ISCA 2016, if you're interested in it. Kevin Shea is the first author. But yes, GPUs are another place where you could benefit a lot from this, because memory bandwidth is a huge bottleneck. Yes? Sure. Mm-hmm. So the idea is fundamentally based on chart sharing. Any memory that is capable of this sort of chart sharing will benefit. And actually, almost all memories, well, all DRAMs clearly have the structure that I described. Fundamentally, there's no difference between a DDR-X memory, LPDDR-X memory, high bandwidth memory, or hybrid memory cube. Fundamentally, their chips are exactly the same. Their interfaces are what's really different. And this is not really changing the interface, at least adding new stuff to the interface. It's really doing things inside the chip. So it's applicable to any DRAM for sure. And beyond that, it could be applicable to other memories also, as I've said. Other people have looked at that. Okay, this is a good discussion. Any other questions, comments, thoughts? Okay, so we can part for today. We won't have class next week. And as I said, we'll likely not have class next week, but please make sure you get your preferences in. And then we'll start scheduling. Scheduling the presentations. We'll be in touch over email for sure. Okay? basically, what we will try to do is we'll try to give you the highest choice that you have in terms of the papers that you've decided. And I think, hopefully, unless everybody is contending on a single paper, we'll be able to honor that, hopefully. And then we'll try to schedule paper and person to the slots that we have in the future. Hopefully, the slot we assign you, you will be available. If there is a really hard constraint, let us know after we assign you, because that may not matter before. Does that sound good? Okay. Okay. We'll be in touch over email then, and I'll see you sometime when we schedule the next class.